And that is Marius Hart, and he is going to be giving a talk titled "The Different Mechanisms That Distinguish Motor Skill Acquisition from Adaptation."
All right, thanks, Adam. I'm actually going to talk about aiming evokes explicit motor adaptation. Let me minimize this.
Sorry about that, Marius.
There we go. Okay, so why am I talking about aiming here? You've seen a couple of talks where we talk about implicit and explicit learning, and it has been assumed for a while back that most motor learning is implicit, but there's actually very good evidence that there's a lot of explicit learning going on, especially in like these mirror reversal paradigms, for example. And often this is being measured with aiming. That is, you ask participants on every trial to think about where are they going to reach towards the target that you're presenting them. And to me, this has always seemed like you're giving people a clue, like the direction of the movement is very important. Maybe this is how you should solve this problem, which makes them more explicitly aware than they would usually be. So when we started looking at like we're very interested in these implicit mechanisms, but we want to make sure that what we're measuring is not due to explicit learning. So instead of using aiming, we decided to use the process dissociation procedure. Now, this is kind of what Shana talked about by using no cursor reaches that either include or exclude the strategy. But then when we are submitting our papers or presenting our posters, then our colleagues are asking questions like, why don't you use aiming, or why don't you find explicit learning with a 30-degree rotation? Because that's what's being shown with aiming. And to me, that is because like we don't want to elicit explicit learning. We want to look at explicit learning. We want to look at the implicit processes. And but of course, we have no evidence that aiming really elicits explicit processes. So that's why we decided last year to start doing an experiment with first an aiming group that has 24 participants, an instructed group that we tell exactly this is the rotation and this is how you are going to be able to counter this rotation. And then we also have a control group that neither does aiming nor gets an instruction. So this is what if this is what the workspace looks like, then people would start their reach here at the home position and they would go to one of 8 targets, let's say this one. And then in the aiming group, before they actually aim, they get this arrow and they can orient that however they like to say, like, this is where I'm going to actually move my hand in order to get the cursor onto the target later on. And then all groups also do this process dissociation procedure, where in no cursor reaches, we ask them to either exclude the strategy, where we supposedly only get implicit learning, or to include the strategy, where we get both implicit and explicit learning. So let me show you the paradigm and data, the reaching data. So first we start with an aligned cursor, and this is cursor training in these 3 blocks. And we have baseline no cursor blocks as well. And then in the rotated parts, they train a little bit longer. And we have, let's say, exclude strategy blocks and include strategy blocks that we can then compare. Here's the data for the control group. It's a typical learning curve with some decay in the no cursor blocks, nothing special. Then we have the instructed group that starts off at about 20 degrees. So they understood our instructions and were able to apply them at least to some degree. And here's the aiming group that does very similar to the control group. So this is not surprising so far. Of course, we also got these aiming responses from the aiming group, and they look like this. This is not as high of an aiming response as you would see in some other papers. It's about 4 degrees. So now let me talk about how the reach after effects we measured relate to this aiming. So here on the y-axis, I'll show what I call explicit learning, and that is the difference between include and exclude strategy. No cursor trials. There, exactly. So here's the control group, which is very close to 0, although not exactly 0. and the instructed group, which is which like they know a strategy because we told them and they're able to do that. And then we have an aiming group, which is, I don't know, somewhere in between. But you may also notice that the distributions of individual participants, that's these dots, are very different for the three groups. So for the aiming group, it looks like there might be a bi-modal distribution. So first of all, here are the distributions for the control and instructed groups, and you have clear peaks around 0 and around like, what is that, 18 degrees. And for the aiming group, there's like two kinds of participants. There's 2/3 of participants are very similar to the control group. It looks like they don't do any explicit learning, whereas 1/3 approximately has about the same explicit learning as the instructed group. So you might already say like, okay, doing this aiming makes some participants explicitly aware just as if they had an instruction. And if that is the case, then the measure of aiming, the aiming responses itself, like the deviations of those arrows from the target, should be similar to this explicit learning mechanism. So that's what I'm showing here, only for the aiming group, because we don't have aiming for the other ones. Here's the individual participants, unity line, and a regression. So, which is not different from unity and highly significant. Okay, so what does this mean? I think, first of all, I don't want to stop people from using aiming. It's super useful, especially if you're interested in explicit learning and if you want to continuously measure it, keep doing that. But we are not, like in most of our tasks, we are interested in implicit processes, and then this might be a good reason to use another method and to decrease the explicit learning and really be able to focus on that implicit process. Exactly, and so yeah, so then I have to say, like, all the hard work and the heavy lifting has been done by Aruj. Thank you so much. And if people want to assign blame or criticize the study, then you should talk to me instead. All right, thank you so much.
All right, thank you, Marius. That was a really, really great talk. I think the demonstration of the difficulties with using aiming yeah, seemed like a great point. And hopefully we can have a good discussion about it here. So you've got a question in the Q&A. Doesn't say whether they would like to be brought on, so I'll just ask it for them. Can you please elaborate on the small magnitude of implicit learning compared to other papers?
Right, well, I didn't actually show the implicit learning. The implicit learning here is about 14 degrees. If you just look at the, so the graph, let me share the screen again. There we go. No, come on. So this is not implicit learning. That is the difference between explicit and implicit reach after effects. So basically, this is the explicit component. But if you really look at the implicit component itself, it's about half of the learning that people did, 14 degrees, or no, 12 to 14 degrees, something like that.
So the implicit and explicit is usually super additive, right?
Yeah.
Or is it usually sums to more than, or to less than it would take to fully compensate? Am I? Or what they fully end up compensating?
Yeah, that's what people say. So I actually, it's good that you bring this topic up. I have this extra slide here with an alternative view on the data. So if like this is your home position and this is your target, then aiming is supposed to be, and then you have what people actually do during training, these reaches, that's their actual reach. And then usually what people do is split up this bit in, like, this part is explicit and that part is implicit. So in other words, total adaptation has to be the sum of implicit and explicit. And if you look at what the experiment does, then, which we program in an algebraic way, then that is correct. But I'm not sure if the brain would solve this particular problem in an additive way. If you do assume it, then like adaptation minus explicit should give you the implicit measure. Or the way we're doing it with PDP here is the include strategy minus exclude should give you explicit. I don't know if either one is true, actually. So let me show you our data here. So this is the total adaptation at the end of training for all three groups. which is the, kind of the same. This is the exclude strategy reach after effects for all three groups, which is also the same. So that means if you take this, this assumption that it's purely additive as true, they should all have the same amount of explicit learning. But even in like the aiming group, the include strategy doesn't get you all the way up to the total adaptation. So that it's not the case for the aiming group that this is additive. Now for the instructed group, it is kind of true, but that might be an artifact. And here for the control group, it's even less true than in the aiming group. So I'm not so sure if we should be thinking of the brain as doing simple addition. It might be a different type of process.
Yeah, sorry, go ahead.
Yeah. So there's also a, I don't know if it's already published, but it's a brilliant preprint by Jana Marius, Susan Werner, and Ofer Danchin that says there are different types of explicit learning that you can measure differently with like these different measures. And maybe there's even like some, I don't know, dark matter of adaptation that we just can't measure with these methods. Right?
Yeah, it seems in particular with aiming that there may be some, perhaps some like calibration error or calibration adaptation that's going on there too. Like you may not have complete access to your aiming in some way. Anyway, I'm gonna let JJ come on, JJ Arban, who is, he's gonna be allowed to talk now. So JJ, you can unmute yourself.
Hi, can you hear me?
Perfect.
Yeah. Hey, Marius. Very clear presentation. So I was wondering how this the exclusion part of the PDP process differs from what has been used by others to measure after effects, simply telling people, you know, here there is a perturbation, here there is no perturbation. And that's what people usually take as implicit, as measure of implicit adaptation. And so I'm not sure exactly how this compares to the PDP, the exclude part of the PDP that you use.
Yeah, the exclude part is more the classic reach after effects. What we add, like Shana did the same thing. What we do is we tell people after they did the aligned part, like remember what you did now, just before, because we're going to ask you to do it again. So reach without your strategy, and then when they do when they're in the rotated part, we tell them like, okay, if you have any strategy, forget that now and do what you did before, which hopefully you remember.
Yeah. I mean, that I guess because what we have been doing is simply showing the target and asking people, bring your invisible hands on the target. It's kind of a different type of instruction. I think it's tries to do the same thing, but it's a different type of instruction. And I wonder whether the instruction can play a big role here. I mean, those are critical, of course.
We actually mentioned the hand too. So it's not totally different, because what in a different sentence we tell people like you have to move your hand to the target, not the cursor. So
right.
What you did to get the cursor to the target, but focus on your hand.
Yeah.
But yeah.
Okay. That's very similar in that.
Great.
Thanks.
Thanks, JJ. I'm going to disable your talking. The session is just about to wrap up, but I will ask Barbara's question. Just for understanding, does this mean that making the subjects report their aim interferes with how they solve this task? Super interesting. So I guess, yeah, if that was going to be like putting a pin in the point here, would you say that that's the summary or the take home?
Yes, for some participants.
Cool. So great question, Barbara, and I think that's